Hi everyone, it's Mr. Vallejo. Welcome to biology class. Today we're going to take a look at the second part of the inorganic chemistry lecture. Last time we took a look at atomic structure and, uh, and, and specifically the atomic models, and we learned how to figure out the number of protons, neutrons, and electrons in an atom of an element. After that, I discussed bonding and covalent bonds, ionic bonds, and we looked at hydrogen bonding, and also we looked at the van der Waals forces or London dispersion forces as well. In this section, I want to take a look at the specific properties of water. So let's take a look at water, and we say that water is the cradle of life. Now, it says here that water has unique properties that are necessary for living organisms. That first property, polarity, is a property that makes all the rest of those properties possible. So that polarity leads to cohesion and adhesion, stores heat, forms ice, the ability for water to dissolve things, and then also it buffers any changes in pH. So let's take a look at these topics. First of all, here's polarity. And with polarity, here's the thing with water. Water is a very polar molecule because it has right here two hydrogens and an oxygen. Let's say that we cut this right in the middle, or maybe if I could picture a dotted line, maybe like right across there, I would see two hydrogens on the bottom and one oxygen on the top. If you just take a look at the nuclei though, a hydrogen nucleus has one proton, but there's two hydrogens. So that'd be two protons. And over here, this oxygen, as you know, has an atomic number of 8. So it has 8 protons. So there are 8 protons here and there are 2 protons underneath the midline. Well, if you're an electron, and you're going across these covalent bond bridges. Remember, electrons are negative. And remember what I said last time is that chemistry is like love, opposites attract, right? So the electrons are coming around and going across this bridge, but most of the time they're staying over here by this oxygen. And because they're staying by the oxygen most of the time, right here we have what's called a partial negative charge, and that's over here. Over here, we have a partial positive charge. The whole thing is electrically neutral, but there's sides to it. And so that's why we call it a polar molecule. It's like a magnet. So that is polarity. Now, this polarity leads to other properties. One property is cohesion, another one is adhesion. Cohesion is when water sticks to like molecules. It's like a sports team, it's like the Lakers are a very cohesive basketball team. You know, they stick together because they're all wearing the same like uniforms, and they all know how each other play, and they're a team. So that's cohesion. So when you have a cohesive molecule like water, one thing that it does is it leads to surface tension. Now, surface tension is when in water you would have an inward pull of the molecules, because what happens is that the polarity leads to hydrogen bonding, and hydrogen bonding leads to this surface tension. It says here insects can walk on water due to the surface tension created by the cohesive water molecules. Those water molecules are not just sticking together in the covalent bonds of the H's and the O's, but each individual water molecule, it has an intermolecular attraction to other water molecules. In other words, the water molecules are the whole molecule is slightly interacting with other water molecules. And so that causes like a little layer on the top where you have some surface tension. So it says here, insects can walk on water. Some insects can, like this one here. This is called a water strider because it walks on water. Some people call it the Jesus bug. Can you see why? And obviously it's walking on water. And if you look very closely here, the insects usually have like hundreds, if not thousands, of little teeny hairs like that help spread the weight of the water over a much greater surface area. That's another thing that happens so that this can happen, that the insects can walk on water because of the surface tension and because some of the adaptations of this animal. All right. Another property is adhesion. Now, adhesion is when water sticks to things that aren't water. Water sticks to unlike molecules. Okay. So due to hydrogen bonding, water molecules can move from a plant's roots to its leaves. In fact, without adhesion, which leads to capillary action, the water wouldn't move up the plant. They say that if a plant didn't have teeny tiny straw-like tubes in it, that water would only go up a plant maybe 4 feet. But you know, and I know, and you live very close to, many of you, the sequoias, and you can see these massive trees. If you were to go to Northern California and the redwood trees, man, those are maybe not as large as the sequoias, but they are certainly tall. And so some trees can get very, very tall, 150 feet or even higher. And how do we get the water up there? The water gets up there through these small tubes. And what happens is something called capillary action helps with that because water moves up a small tube. And you can see capillary action in a straw, just ever so slightly. What you could see is that in this straw right here, what you would see is that the liquid pressure would push down, okay, on the surface of the liquid, and it would go up the straw a little bit, just a very tiny bit. But the level of the liquid in the straw is higher than the level of the liquid in the whole cup, and that's capillary action. So water can go up a plant due to capillary action. There are also a couple of other things we'll talk about later. There's a process called transpiration, which is a loss of water through the leaves. And then also there's what we call the surface tension and the capillary action, all these things, the transpiration, all of these things work together. Also, the amount of water inside the soil is greater there than it is at the top of the plant. So water is being pushed from the bottom up. So that's some of the basics of how water goes up a plant. All those processes are working together, but we'll study those a little bit later when we take a look at plant biology. All right. Water also stores heat, okay? And my picture at the bottom is of some condos at the beach. And a lot of people like to live near a beach. And why is it so nice by the beach? Because of the climate. And the climate is pretty stable, and you don't have massive changes. If you were to live in a different part of the country, my mother-in-law lives in Eastern Washington. There's mad changes in temperature, and so sometimes it'll be 10 degrees hotter there than it is where I live, but then during the winter it'll be 10, 20, 30 degrees lower there than where I am. And I live about 20 miles from the ocean. So water has a lot to do with that. And so it says here, water stores heat and it takes a lot of energy to break the hydrogen bonds. So water is able to absorb a great deal of heat energy without a large increase in temperature. And that's why the temperature is so stable. As water cools, a slight drop in temperature releases a large amount of heat. So Those are the properties. That's another property of water that it stores heat, and this leads to these other properties of waters that have to do with the same topic. So let's look at these. High specific heat forms ice, and high heat of vaporization. Okay. Now, high specific heat, this is a chemical, a chemical definition in chemistry. We say that the specific heat of a chemical is the amount of energy that is required to raise the temperature 1 degree Celsius. Okay. And it's the material, the amount of material is 1 gram. So, so water, compared to other chemicals, has a high specific heat. Well, what makes it have such a high specific heat is because of again, the polarity and the hydrogen bonding that forms between between the different water molecules. And I wrote, moderates climate and body temperature. This is a picture of some people in my family. It's my oldest son, Joshua. Yeah, it's my second oldest son, Adrian. It's my third oldest son, Raul. And then this is my oldest daughter, Destiny. And then this kid right here, I don't know that kid. Just playing with my kids. But this is at the beach in Huntington Beach, California. And my mother-in-law used to live, before she lived in Eastern Washington, she used to live a block from the beach. So I used to park at her house and walk to the beach. And so we would go to the beach a lot because we had free parking. And and then when we went to the beach, though, I always say, bring a sweatshirt, because the temperature would drop a little bit, but not so much. You don't need a parka or a really thick coat. Just a sweatshirt will do it, because it might be 72, 74 during the day, but it gets down to 65, maybe 60 at night, not a big change. On the other hand, I've camped in the desert before. I camped because when I was working on my second degree in biology, my master's degree, we had to spend more than 2 weeks out in the desert. And I remember my teacher would take us out to a patch of desert, about 20 of us biology students, and then she would say, okay, you have an hour and a half, classify every plant in this area. What? And so those are the types of things we did in the desert. We trapped kangaroo rats. We hiked over to a riparian stream. We did all kinds of things like that. So it was pretty cool stuff for biologists. But camping, though, I remember pitching a tent at 11:45 at night, and it was really cold in the desert at night. It gets down to almost freezing, depends on the time of year. I was there in spring, and it was really cold. But then, during the daytime, on a hike, it got over 100. So it goes from 35 to like 105. So why is there so much change in heat or change in temperature over the desert compared to the ocean? Well, in the desert, what you have no clouds. These clouds are like a blanket, and all the water there. Remember, water has a high specific heat, so the energy is going to be absorbed, and it's going to be used then to change to break those intermolecular bonds, those hydrogen bonds, before anything happens. So water has a high specific heat. Water also forms ice with a decrease in temperature, which is unusual in the sense that the ice is less dense than liquid water. When water forms a solid, these water molecules spread out because of the hydrogen bonding again. But the liquid form, because these guys have more energy, they break these bonds. Look, there's no bond between these guys right there. And so because that happens, we have some bonds forming, some bonds breaking, and these water molecules are closer together. So that's the liquid molecules are actually closer together than the water molecules that are in the solid form in the ice. That's unusual. And so this unusual, unique property leads to the formation of ice and the ability uh, of animals like fish, organisms to live underneath the ice all winter long. It says here, floating ice protects lakes and oceans from freezing solid. Because the ice forms and it sits on the top. And because it sits on the top, then these guys are, the fish can live underneath the surface all winter long. Okay, and so let's see. Actually, this is a picture that I took before we had cell phones, before flip phones even. I was on a camping trip maybe 20, 30 years ago, and I was in the Eastern Sierras, just north of Bishop and just before Mammoth Lakes. But there's a bunch of other lakes here. This is actually Lake, I think it's Convict. And at Lake Convict, I was looking for my kids. Actually, my father-in-law had taken two of my boys fishing a couple of days ahead, and then when I got there, I was looking for them, and it was 2 or 3 in the afternoon, and I was just looking all over the place for them because they left a note for me at the campground that said, "We've gone fishing. Come and join us." But they didn't tell me where, and there were so many lakes around there. I had gone to 6 or 7 different lakes, and I didn't ever see them. So I went back to camp and got set up. But they told me that they were actually at the second one that I went to. Oh, I just didn't see them. Anyway, what happens is that ice will form on top of the lake, and then organisms can live over winter. If ice formed in the different way, if ice was more dense and it went to the bottom of the lake, then the lakes would never thaw out, and so that wouldn't be possible. That wouldn't be, life wouldn't be possible if that happened. All right. Some of you know this young man. This is Lamar Odom. He played for the Lakers. He also played for the Heat in Dallas. I'm a Laker fan, but I kept the picture of him in the Heat uniform because it has to do with this slide that says high heat of vaporization. Now, Lamar Odom in his prime was a 5-tool basketball player. You could play center, you could play point guard, and everything in between. He's a well-oiled athletic machine. But I saw him work out once before a Laker game with those funny-looking rubber band things. Have you seen those? But before the game even starts, this guy's sweating it up like this already. That's because he's, like I said, a well-oiled athletic machine. Because when you're sweating, what that does is that it takes away a lot of energy. When it evaporates, then that takes the energy away, and it leads to what we call evaporative cooling. Some some organisms will do this a different way, and they will, like birds, flamingos will actually, what flamingos, you might think of a flamingo standing on one leg. I used to work at the zoo, and before we even got to the zoo, before we even saw the flamingos, you could smell the flamingos. And so what flamingos will do is, sometimes if you watch them for a long time, they'll actually look like their waste products are going all over their legs. It's like, hey, you're not aiming very good. So, but actually what they're doing is they're trying to cool themselves, which is kind of a little silly, right? But if it works, it works. Other birds have a different mechanism by their throat that they move back and forth, and it has a little bit of moisture in it, and then that evaporates and it cools off also, so called a gular. And then when it moves back and forth, it's called gular flutter. But high heat vaporization, just a small amount of sweat is going to take a lot of energy away. That's because of the properties of water. All right, another thing that water does is water dissolves things quite well. That's because most things have either a positive or a negative charge. And you can see in this picture here, this is there's some salt at the bottom of this beaker, and this represents the salt crystal. And the water molecules, the red oxygen and the two hydrogens, are surrounding the individual atoms of the salt molecule. And it doesn't matter if the ion is positive or if it's negative, because remember, water has a slightly positive and slightly negative side. So over here, this is the slightly positive side of water surrounding this ion. And then this one has the oxygen, the slightly negative side surrounding this positive sodium ion. So no matter if it's positive or it's negative, water's going to surround it. And then this then can mix with the rest of the water molecules and form a solution called an aqueous solution. When you have a water-based solution, that's called an aqueous solution. Now, don't mind the text over here, but this is two separate diagrams. And what you see is these blue molecules are better off if they stick together like this, because they're being surrounded by water. But this part right here is protected from the water because they're binding together in a way. They're not really, it's not a chemical bond. It's more like they're clumped together. And because they're clumped together, then only the outsides are exposed to water. So it's going to minimize the exposure of these methane molecules to the water, and that's called hydrophobic interactions. You look at the word hydrophobic, hydro has to do with water, and phobic has to do with fear. So this is fear of water. So water will take and organize non-polar substances like methane, and it'll make them stick together like that. So water has a lot of different properties, including influences on other molecules. Now, water will also buffer a solution because water will turn into ions. What will happen is the water molecule, remember, is H2O. And so if it's H2O, sometimes the H splits off and then the OH is left. Well, if the H splits off, it becomes a positive hydrogen ion. And then this over here, OH minus, called the hydroxide ion. Or hydroxyl ion, and the hydroxyl ion and the H plus there. This is the scale. This is called the pH scale. It goes from 0 to 14. Now on the edges, 0 to 14, those are chemicals that are really caustic or very, very acidic. You can see over here some of the examples of the different chemicals. As you go from 7, and it's like the earthquake scale. Every time you get a change, it's a change by an order of 10. So if you have pure water where the concentration of H plus is equal to the concentration of the hydroxyl ion, then what happens is if you go from 7 to 6, this has instead of having just saying less or less OH minus and more H plus, the further you go over here, it's an order of 10. So if you go from 7 to 6, that's 10 times. If you go from 7 to 5, that's 100 times. If you go to 7 to 4, that's 1,000 times. So it's like an earthquake. It's a logarithmic scale. So that's pH. And by definition, the pH is an acid releases H plus ions in solution, and a base accepts those H pluses. Now, a base will accept the H pluses, but it'll have more OH minus ions floating around. Okay, so that's the acid and the base scale. So we'll just touch on that here. In biology and chemistry, we might spend a lot of time on this, but in biology, we just need to know that because there are actually influences from acids. You can see down on this chart here. You may have heard of acid rain. And with acid rain, This says here over here, this is it says rain in a remote area. And you would think that rain would have a pH of 7, but it has a pH of around 5, 5.2, 5.3 over here in this diagram, 4.8, 4.9. As you can see, here's some strange conditions, even in some areas that are thought to be pristine, like in the mountains in New York. Look at that, acid rain, 3.2. But look at this, fog in Los Angeles, less than 2. So as we go over here, it gets more and more acidic. Imagine if it was, if you were in this fog, it's like the fog was lemon juice. Or can you imagine the precipitation being like vinegar? And then battery acid is very corrosive. And so you want to minimize your exposure to that for sure. On the slide, it says buffers are substances that reduce or resist pH change in the presence of water. The pH change will be less than it would be if it wasn't in water. So that's called a buffer. A buffer minimizes those changes that you would expect. Okay, so the pH scale. So pH in acids and bases are significant in ecology because acid rain and it could be fog, it could be snow, so we call it acid precipitation. Acid precipitation threatens the environment. You can see what happens here. Here's a big factory on the East Coast, maybe around Pittsburgh. You know, you football fans, you may know the Pittsburgh Steelers, right? So there's a lot of steel plants in that area, a lot of industries like this, and they might have really tall smokestacks. And then the waste from the factories go up in the air. And so instead of just settling down in that city, it spreads hundreds of miles. And when it comes down, then it comes down as acid rain because the sulfur and the nitrogen will react with the water in the atmosphere to form sulfuric acid and nitric acid. And then that's where you get acid rain. In California, we have more of a problem with nitric acid because those are the chemicals that form not from factories, but from car pollution. So especially like in Los Angeles is the smog capital of the country. Actually, one area sometimes takes over the title of smoggiest city in the United States. Sometimes Houston's air is even worse than Los Angeles air. But because of these things that happen here, and acid rain comes down. When acid rain comes down, you get things like this. Here's a picture of a statue 100 years ago and now. Here's some trees that no longer have their foliage, and they're even killed because of the acid rain. And here's a map showing you where the acid rain is a big problem. And so you can see very close to us, say here's the Eastern Sierras where you would have a problem because of all the car exhaust from stuff will go over because of the winds over the mountains. And that's where that settles out there. The location at the capital of the University of Toronto is a very notable place for environmental science studies. And that's right there in the middle of the acid rain region. And actually a very important document was called the Montreal Protocol. And that had to do something with air pollution that was drafted over there. Because if you look, I mean, all the factories are right here. Okay, there's Pittsburgh right there. It's called the Ohio River Valley. A lot of factories right there, but the pollution from those factories, you can see go north and over here to the west. That's where you get all those problems. Okay, all right, more on acid rain later when we talk about ecology, but that's it for today, and these are the properties of water. So thank you for coming to biology class, and I'm Mr. Vallejo, and hope you have a great day. Okay. All right.